Dear students, today we'll be taking up one group CX disconnections, which we had done earlier in class. As I had been asked as to why I had moved on to the other disconnections, the two group disconnections and difunctional disconnections. This is because we had done this in class earlier, so I thought I would take it up after we had completed the other units on disconnections. So now this is the simplest of the disconnections where we are taking into consideration the disconnection between carbon and a heteroatom. Disconnection between carbon and a heteroatom will lead to obviously the heteroatom getting the negative charge and carbon the positive charge. So obviously when carbon gets a positive charge and the heteroatom is a negative charge, we are in other words looking for disconnections which are taking into consideration nucleophilic substitutions. So generally, it should be such that we are able to connect it or synthesize that molecule knowing our chemistry. So always the leaving group will be such which is a good leaving group. That is, the disconnections will be such where X is a good leaving group. So we can get the best reagents from such disconnections. Now this is RCOX, and RCOX is an acid halide. So the acid halide naturally when disconnection will give us those reagents which undergo substitution easily. On disconnection we'll be getting R positive, which will be balanced, the C positive balanced by the Y negative. Now the Y can be any good leaving group like Br or tosylate, etc. Here Y and X negative is balanced by H positive. Now taking the example of this target molecule as is shown, this is an ester RCH2COOR dash. And the disconnection between the carbon and this oxygen, this carbon and this oxygen. Otherwise, if we disconnect it here, then we aren't taking into consideration any functional group. So this is one group disconnection. So what is the functional group? The one functional group which we are taking into consideration while disconnecting the carbon and the heteroatom is this functional group, which is ester. So we have to disconnect and between this carbon and this oxygen heteroatom, not this carbon and this heteroatom. Otherwise, this functional group will leave on the whole. So we have to disconnect with respect to this functional group so that it is broken midway. Now this will give rise to oxygen negative and carbon positive. RCH2O negative. Now we can associate it with an H positive, that will be an alcohol, and RCO, the positive, we can associate it to form the synthetic equivalent with a negative. It can again be an OH, which will be an acid, or it can be Cl. So we need a good leaving group. And we know in this case, when RCH2OH, that is an alcohol, it reacts with an acid also to give us esters. We know this reaction, this chemistry exists. And at the same time, we also know that an alcohol reacts with an acid chloride, an acid halide to give us an ester. And the reactivity for this amongst the acid derivatives is the most for acid chlorides, less so for acid anhydrides, still less for esters, and still less for amides. This is in the acid derivatives. Since here we are going to form an ester and we have disconnected an ester, so this will lead to an acid halide. It could also be an acid RCOH, but this is more favorable taking the acid halide because this is a convenient reaction and it goes about easily, very easily in the presence of a base. So this on connection or on synthesis, that is the alcohol which will react with the acid halide in the presence of a base to give us the target molecule or ester. Now look at this synthesis. The synthesis which I have written here is a perfumery compound. It's also used as an insect repellent, as you must be aware that all compounds which have some or the other odor are also many a times insect repellents. Many such terpenoids are the examples of these, such as citronellol, etc. So this compound here, again having a good smell like the terpenes. It is not a terpene, but this is an ester, and ester we know also are fragrant. This on disconnection between the carbon and this heteroatom. Remember, not this carbon and this oxygen, otherwise we will be removing this entire ester group. Now we are disconnecting the ester. We know how an ester is formed by the action of an acid halide and an alcohol. So this is what is being done. So in this case, now, as was here, once we disconnected this compound, this is the perfumery compound, it is analogous, similar to this, because this too is an ester. So this is C6H5 CH2O C double bond O C6H5. This ester on disconnection will give us this alcohol, and alcohol means, because this disconnection, this heteroatom will be O negative, so H positive, and this carbon positive will be balanced by the Y negative. The Y negative is most of the time a halide. So this will be again a reaction between the alcohol and this acid derivative in the presence of a base to give us the target molecule. This is the RX disconnection. Now let us see the next synthesis. In the next synthesis, which is a disconnection, taking into consideration this target molecule, and this target molecule, as is seen, is a weed killer. Now this target molecule here, which is taken up for disconnection, again a carbon hetero, this is a weed killer by the name of propanil. Analyte, so propanil, because 1, 2, 3, see, these are the 3 carbon atoms. This is actually the commercial name for it. It's a weed killer. It's used in rice fields. And the disconnection, as is obvious with this benzene ring, we will be disconnecting not this or this or this or this, but see, this is the disconnection we'll be undertaking. And on disconnection, carbon heteroatom. So nitrogen negative, carbon positive. These will be the synthons. Nitrogen now positive, NH with another H will give us this NH2. That is the aniline substituted with chloro at the meta and the para position. And this NH2. Now how to disconnect this heteroatom from this carbon? Now this is not all that simple, because we know nitrogen on disconnection will be getting a negative charge. And as we know that benzene rings give electrophilic substitution as a norm. For nucleophilic substitutions, the conditions have to be drastic. So it won't be a good disconnection, because NH2 negative will be a nucleophile, not an electrophile. So is there some way by which we can also remove this NH2, and at the same time our reaction process turns electrophilic? So we do know that if we interconvert this group into another functional group, that is, in other words, functional group interconversion, FGI, and we are aware that NO2 group is one such group which is a very good electrophile, and at the same time it easily is reduced to NH2. So this will be a very good disconnection. So what do? We simply change this NH2 functional group interconversion and write NO2. And now we disconnect the carbon and nitrogen, not here, but here, because we know once we disconnect this carbon and nitrogen, this can be connected back. So now on disconnection, we will get our dichlorobenzene, and this dichlorobenzene will be 1,2-dichlorobenzene will be now our starting reagent for the synthesis. Now the synthesis starting from this dichlorobenzene will first of all undertake nitration, because the last step in disconnection becomes the first step in connection or synthesis. So now on nitration, when this is nitrated, we will know whether it is with respect to this chlorine or this chlorine. It is one and the same thing. We will get, because chlorine is also para-directing, so we will be getting a para-substituted product due to the steric reason now, because this is the ortho position, these two are ortho to each other, so a para substituted nitro product. And moreover, chlorine, as we know, is ring deactivating, so it won't lead to therefore much poly substituted or di substituted or tri substituted. We will be getting this mono substituted product, and this mono substituted or nitrated product on nitration on reduction will lead to the formation of this amine, which on further reaction with CH3, CH2, COCl. See, this was what we disconnected in our RX disconnection. There were there were two RX disconnections in this. Firstly, the RX disconnection for the ester, and the second, the RX disconnection for this CH3 between the CH3CO, CH3CH2CO and N. So now this again will be reacting CH3, CH2, COCl with NH2, so that HCl is eliminated and we get our target molecule. Rx disconnection, remember this is a one group disconnection. We are disconnecting taking into account the presence of only one functional group. Now this other disconnection which we are taking up seems a little complicated, but is not, because this target molecule here, COH, COO, again we are seeing an ester. So it is not difficult. It's looking a little complicated, but it's very simple in the sense if we disconnect between the ester between this carbon, this will be positive, this heteroatom will be negative. So this will get a negative charge, this a positive charge, and this can again the positive charge be balanced by an OH negative, and this negative charge be balanced by O negative by H positive. So again it will be an alcohol, and this time because we have this COH at the adjacent position and the other COH, and this COH itself will give us a very good synthetic equivalent, that is our phthalic anhydride. So phthalic anhydride, because on reaction or synthesis with this alcohol in the presence of a base will lead to the formation of COO, an ester will be formed, COO, and this here the alcohol portion, and we will get in the presence of a base R. So again we are doing the RX disconnection, this time taking into consideration the presence of the COH group. So on disconnection we will be getting COO, the CO here, and OH. So this is phthalic acid. So phthalic anhydride, because these two are adjacent to each other, this will be a very good synthetic equivalent, because on reaction will be CO, the ester, and at the same time CO in the presence of a base, the H. So we will be getting our target molecule. The reaction we know and we are familiar with. Now let's see to this next disconnection, which is quite interesting, because this time this target molecule that is being taken into consideration is interesting in the fact that it's an ether. So it can be disconnected. It's again a perfumery compound, C6H5CH2O, CH2, CH2, CH3CH3 with an isopropyl end. So this perfume can recompound, it can be disconnected. As we can see, there are two carbons on either side, and the functional group here we are taking into consideration is the ether. So it can be disconnected between this carbon and this oxygen, or it can be disconnected between this carbon and this oxygen. Now, if we disconnect it from using this pathway A, that is C6H5CH2 O negative, this here H, that is it is disconnected after oxygen. Here in this case we will be getting C6H5CH2OH, and since we O negative, the disconnection between this carbon will lead to carbon positive. So carbon positive will be balanced by an X negative. So this is path A. Now at the same time it can be disconnected here as well. So here if it is connected, we will get C6H5 CH2X, maybe it can be Cl also, a heteroatom here, and this is OH. So see, there are two pathways by which this can be disconnected because it is attached to carbon on both the ends. So it can be Rx disconnection this way, which is pathway B, where we will get C6H5CH2Cl, or it can be pathway A, where we will get C6H5CH2O, and then it will be this this end, that is this branched end, which will be changing into the halide. Now, which of the two is the better disconnection? Because we have got two options. As we know that when we are disconnecting it in this way, so what type of a substitution will take place by using pathway A is, because C here will be getting a positive charge, and this will be a good leaving group, the X. But C, a positive charge implies, since it has got a branched end, so it will try to lessen the steric strain. So there will be a competition between the two. As we know, carbon positive here will therefore lead to elimination as well, because the elimination will be favored since the steric strain at this end will be reduced. So this will lead to a positive charge here, elimination of H positive, and formation of a double bond. So this will be the competing reaction with this. Hence, what is the other option? The other option is to choose this connection, this type of, where we will get CH2 positive. And since we know with the CH2 positive this time is attached to an aromatic ring, so there is no chance of forming any rearranged product or any elimination. Here when the reaction takes place, of course it will be SN2 type of reaction because this is a primary halide, then elimination will also occur at the same time. In this case, as this, it will be competing with this, because these are bulky groups, these are groups which are attached here. Hence the pathway B will be the preferred pathway. In other words, because this now will be the nucleophile. When this is the nucleophile, in that case this carbon here positive will no longer be competing for any type of elimination reaction. So this is the preferred pathway. Now, taking into consideration this retrosynthesis or this disconnection, again the one group CX disconnection. See the one, and this is known as chlorobenzene. This is used for killing mites. So the commercial name is chlorobenzene. Now, as we can see, again, this is attached to carbon at this end and carbon at this end. Now, if we disconnect it at this end, we will be getting S negative. S negative means again a nucleophile. And as we know that aromatic rings give electrophilic substitutions very easily. not the nucleophilic ones. Those are not the norms. So to connect this S negative back to this ring is not something simple. It requires drastic and modified conditions of the ring so that it gives nucleophilic substitution, because this S negative will be a nucleophile when it is disconnected, because this is a heteroatom. So we won't disconnect it between this carbon and this sulfur. We will disconnect it between this sp3 hybridized carbon and this sulfur. In this case, now when this gets a negative charge, this will be positively charged, and again this will be not an electrophilic but a nucleophilic substitution. So you know why the disconnections is not made between this and this, the aromatic ring and this heteroatom, because this will lead to a nucleophilic substitution here. And aromatic rings do not give nucleophilic substitutions, only under drastic and modified ring conditions. Therefore, we disconnected between this alkyl group CH2 and CH2 here and S here, heteroatom here, because the alkyls give nucleophilic substitutions very easily. As we discussed in the start of this unit, that basically when we are disconnecting carbon and a heteroatom, carbon will be positive and the heteroatom obviously will be negative. So while connecting it or synthesizing, we are looking for what? We are doing what? We are doing a nucleophilic substitution. Hence, this is the disconnection. So now this will lead to CH2 positive and S negative with an H positive. So this will be SH thiol. So this is the synthetic equivalent in this case, and here CH2 positive, Cl negative. And now we can connect it easily. It's in the presence of a base, H positive from here with Cl. Now remember, it is not the Cl, because again, how can this Cl be eliminated from here? It can't be substituted. It will be this Cl, nucleophilic substitution. So because this is sp3 hybridized carbon, this is the aromatic ring. So it will not be this which will give the nucleophilic substitution. It will be this part which will be giving us the nucleophilic substitution. So this will be the nucleophile, S negative, H positive with the base, it is easily removed, and this S negative therefore attacks this carbon, because this chlorine is pulling electron towards itself and will be a good leaving group, leaving the carbon positively charged, attacked by this nucleophile, giving us a good nucleophilic substitution reaction and hence formation of a target molecule. So this was a simplified form of the easiest of the disconnection, that is our RX or CX1 group disconnection, taking into consideration the presence of just one functional group in each case. It can be an ether, it can be sulfur, it can be an ester oxygen. So this was all about this disconnection.